Hello, everybody. We should be live. Let me just quickly check. I also want to check audio. So, yes, we're live. Yes, we are live. Let me just quickly check. I also want to check audio. So, yeah, the audio is good too. So, we're good. Okay. Real talk. I have been slacking in life. I haven't studied or worked properly last week. I'm actually in Visakhapatnam. Last stream I was actually in my last stream I was at Bangalore airport, and ever since I came back I didn't study much, and I've been keeping it chill. I'm also excited that I am in my room, in my hometown. This is where I studied for a really long time. So this is my room, and why is it blurred out? It's not clean, but I'm a little excited. This is a nice setting. That's my grandfather's picture. So yeah, that's been happening, and I thought I shouldn't be resting too much, and today we will do some stuff. Again, like any other stream, I don't think I have a nice agenda, but I've been looking at this course, and I don't think it can be useful. It might not be useful, but
etc.
I'm also on single monitor, so it makes things a little tricky because I have to keep switching tabs. But yeah, maybe we'll start with this course and see where things go. If not useful, maybe we'll do something else. But I want to start with this
structure and didn't really fit into rows and columns. We need.
Before that, so a friend of mine, actually a colleague of mine, did this course, and I was a little excited to do it myself, and that's why I put it up. And yeah, this course was available on LinkedIn, and I didn't have LinkedIn, so I found somebody on Reddit, and I pinged them on WhatsApp, and it was a little suspicious because they were asking for they asked for $200. They said okay. I pinged somebody on WhatsApp, and they said that the course was going to be 2,500. Then I bargained it for 1,000, and it was 1,500. Then it was 1,000. Then it came down to 1,400, which is fine, because the course was LinkedIn Premium actually cost 500 rupees per month for the first 2 months, and then it goes up to 1,000 rupees per month, which is a lot. And I thought even 1,400 per year would be fine, and I pinged him, and I paid him 200. Then he as an advance, and he sent me link, and once I got that link I signed up. And let me actually pull up that picture. Pull up that picture. So if you look in this picture, he says it is premium only for 3 months. So I was a little sus, and I was like, are you giving me 3 months plan, or you said it was a 12-month plan? So there was some bullshit that was happening, but somehow at the end of the day I paid him $1,000, and I got this premium, which is supposed to last for 12 months, but worst case it might only last for 3 months, but we'll figure out. I have access right now, and that's why I just wanted to give you a little backstory on how to get LinkedIn Premium at a discount.
We needed a solution that was agile and diverse as the data itself. Enter Apache Hadoop, inspired by the Google MapReduce and Google File System papers. Hadoop was designed to store and process huge amounts of data across clusters of commodity servers. It democratized data storage for many, allowing for the storage of data in its rawest form across distributed environments. This was the conceptual beginning of what we will soon call a data lake. The term data lake itself was coined by James Dixon, CTO of Pentaho, around 2010. He used it to describe a large repository of raw data held in its native format until it was needed. Unlike data warehouses, which we will talk about a bit later in this chapter, data lakes were designed to be agile, scalable, and capable of handling the complexity and nature of real-world data. The evolution of data lakes is also closely tied to the rapid advancement of cloud computing. As cloud services like Amazon Web Services, Microsoft Azure, and Google Cloud became more robust, they provided the perfect ecosystem for data lakes. These platforms offer scalable, secure, and cost-effective storage solutions, allowing companies and teams of all sizes to set up data lakes without the need for expensive on-premise infrastructure. The concept of data democratization, making data accessible to everyone without gatekeepers, is another key factor in the rise of data lakes. By allowing data to be stored in a central location that is accessible to different stakeholders within a company, data lakes enable a collaborative environment where insights and decision-making are available across departments. So there you have it. A little bit of history to understand how we arrived here, and maybe even think about what the future may hold. Ever wonder what lies beneath the surface of a data lake? Let's take a high-level overview to their main architectural components, or layers, and explore their main characteristics. These layers go from the least actionable at the bottom to the most actionable at the top. This is so important that I actually have structured the rest of the course to go in this order. The storage layer is the foundation of a data lake. It is designed to hold an enormous amount of raw data in various formats, from structured to unstructured. This layer must be highly scalable to accommodate growth in data volume without degrading performance. There are three main characteristics that a storage layer should have. It should be able to expand easily to store as much data as you need, and that could be petabytes or even exabytes of data. It should be optimized to keep the cost manageable, especially important as data volumes grow. And lastly, it should be able to support multiple data formats and structures. Next, the ingestion layer handles the intake of data from various sources, whether it's streaming in real time or in batches. It's fundamental for preparing and moving data into the lake in a consistent and reliable manner. The characteristics of an ingestion layer are, first of all, it should ensure data is accurately and reliably collected without loss. It must be capable of handling high volumes of data at high speed, and as you may imagine, it must also support different ingestion methods to accommodate diverse data sources. After that, the processing layer is where data is transformed, aggregated, or joined. This layer allows for the application of business rules and data transformations to derive insights from the raw data stored in the lake later on. This layer can be seen as part of the ingestion layer or separate. In this course, I structure them together under the same chapter because they are often orchestrated and managed together. The characteristics of the processing layer are as follows. It must be optimized for fast processing of large datasets. It should support several processing needs, from batch processing large datasets to real-time analytics. Lastly, it must be capable of scaling out to meet your processing demands as data volume or complexity increases. Second to the top, as its name suggests, The management and governance layer ensures that data lake remains organized, secure, and well-managed environment. It includes aspects like metadata management, data cataloging, security, and compliance. The following are characteristics of a solid governance layer. It should provide mechanisms for data access and authorization to secure sensitive data. It also should allow you to track data lineage and metadata for transparency and auditability. And it must ensure data management practices meet regulatory requirements. And finally, the analytics layer is where data becomes actionable, providing tools and interfaces for end users to query, visualize, and analyze the data stored in the lake. This layer delivers the following. It provides user-friendly tools for data access and analysis. It ensures compatibility with different BI and analytics tools, and is normally optimized for quick and efficient querying. When one hears the term data lake, it is easy to assume we are talking about just a huge data repository. The truth is that it is a complex structure with several moving parts that make it a super powerful data management system. By now I have mentioned data warehouses a couple of times, so you may be wondering, what exactly are the differences between a data lake and a lakehouse? Let's clarify that. First, let's formally define what a data warehouse is. A data warehouse is a system used for reporting and data analysis, and is a core component of business intelligence. It stores current and historical data in one single place. This data is typically loaded from transactional systems and other relational databases, and is structured in a way that makes it easy to query and generate reports. Now let's review some of the key architectural differences of data lakes versus data warehouses. In terms of data structure, data warehouses are highly structured and use a defined schema to organize data into tables, rows, and columns, which enable really fast access through SQL queries. This structure is ideal for complex queries and generating reports, as I mentioned before. Data lakes, as mentioned previously, store data in its raw format without a predefined schema. They use a schema-on-read approach, where data is structured when queries are executed and not when data is stored. This allows for more flexibility when working with diverse data types, where data is structured when queries store data in its raw format without a predefined schema. They use a schema-on-read approach, where data is structured when queries are executed and not when data is stored. This allows for more flexibility when working with diverse data types, from structured data to unstructured data like emails, images, and social media content. In terms of storage philosophy, data warehouses normally require data to undergo extensive cleaning and transformation before or after it is stored. This helps with data quality and consistency, but it can be time-consuming and inflexible. Data lakes often allow for the storage of data in its raw format, with no upfront cleaning. This means they can quickly ingest huge amounts of raw data, providing flexibility but requiring more processing power to access the data than a data warehouse would. Regarding storage technology and cost, data warehouses typically use relational database management systems that are optimized for fast retrieval of structured data. Data lakes are often built on technologies like Hadoop or cloud-based object storage solutions like Amazon S3. Object storage can be significantly cheaper than traditional database storage. Regarding data accessibility and use cases, data warehouses are accessed through SQL queries, making them suitable to business intelligence professionals who need data in a readily consumable format for decision-making and reporting. Data lakes, on the other hand, require additional processing tools to organize and analyze the data stored in them, such as Apache Hadoop or Apache Spark, making them more suitable to data scientists. Data lakes are better suited for exploratory data analysis, machine learning, and artificial intelligence. I hope things are more clear now. In the next video, we will compare data lakes to another modern data management concept, data mesh. A term that has gained popularity in the last few years is data mesh. But what is it? And how does it compare to the data lake? When I first heard of data mesh, I was really confused as well. So let me try to clarify things for you. Data mesh is a relatively new architectural concept that views data as a product. Unlike traditional data management approaches that centralize data governance and architecture, data mesh promotes a decentralized approach. Here, data is owned and managed by domain-specific teams who treat their data as a product, ensuring it's usable, accessible, and valuable to the rest of the company. So a data mesh is not a specific technology like the data warehouse or the data lake, but a complete methodology for data management inside a company, which involves technology and people. Now let's compare a data lake to a data mesh on different levels. In terms of data governance, a data lake is centrally governed, typically by data engineering teams that manage access, security, and quality. This can potentially create delays and inefficiencies in a data access and use. With a data mesh approach, each domain or team manages their own data as a product, which includes responsibility for quality, governance, and sharing data across the company. In terms of architecture philosophy, a data lake is a centralized repository that stores enormous amounts of unstructured and structured data, so it is a single place where data from different sources is stored. A data mesh, on the other hand, focuses on decentralizing the ownership and architecture of data. That means that some teams may use a data lake, while others may decide to use a data warehouse and so on. It aims to avoid bottlenecks and governance issues that can arise with centralized systems. Regarding use cases, a data lake is ideal for centralizing data storage where everyone can access and analyze it. Data lakes are better suited for companies that need a large repository to perform analytics and want a centralized control over their data environment. A data mesh is normally adopted by organizations with complex data from different business domains, where domain expertise is essential for managing and analyzing data effectively. This could be a large retail company with separate teams handling inventory, sales, marketing, and customer data, each team needing specialized knowledge to manage and make sense of their specific data sets. Because of this, a data mesh is more suitable for large, distributed organizations with autonomous teams that need to manage and use their own data in an agile way. I hope this short description and comparison has clarified doubts about data mesh. It is a novel and interesting concept that generates both excitement and skepticism in the data community. I'm curious, have you seen it applied successfully in a company?
Let's go. Questionnaire. What is the key characteristic of data lakes that makes them relevant in modern architecture? Yeah. It actually decentralizes. This processing, not storage. I'm sorry, I'm not talking much. I'm locked in.
In a data lake, the storage type you choose plays an important role in how data is maintained, accessed, and used. Understanding these types is very important because it can help you optimize your data strategy to balance cost, accessibility, and performance. Let's explore the main types of storage used in data lakes. Object storage is by far the most important storage type for data lakes, especially in cloud environments. Here, data is stored as distinct units or objects, each with a unique identifier which allows you to retrieve from a distributed pool of storage resources. This type of storage is highly scalable and cost-effective, making it ideal for storing huge amounts of unstructured data like photos, video, and large datasets. Examples include Amazon S3, Google Cloud Storage, and Microsoft Azure Blob Storage. File storage organizes data in a hierarchy of files and directories, allowing you to access and manage data in a way that is familiar to most computer users. While it is not as scalable as object storage, file storage systems like network attached storage or NAS are often used for smaller scale or legacy applications that require traditional file system interfaces. Block storage divides data into evenly sized blocks, each with its own unique address, but without any metadata to provide more context about the content. This type of storage is often used for performance-intensive applications like databases or ERP systems. It can be more expensive and more complex to manage though, making it less common for general data lake usage. Data lakes could also integrate hybrid storage solutions that combine elements of object, file, and block storage. These solutions are designed to offer the flexibility of object storage with the performance benefits of block storage. For example, Hadoop Distributed File System, or HDFS, or other software-defined storage solutions can manage data across different storage types effectively. As you can see, each type of storage in a data lake has its own set of advantages and ideal use cases. You can tailor a data lake architecture that meets your own specific needs and challenges by selecting the correct type, ensuring your data is stored efficiently. So far, we have talked about how to store data in a
I
data
feel
lake.
sleepy.
And now it's time to talk about where. As diverse as
Also going slightly off track, but my sleep schedule has been FUBAR. FUBAR is a new word that I had learned. Fouled up beyond recognition, but it is not fouled. This is it. This is what has happened to my sleep schedule. My sleep schedule is FUBAR. I've been sleeping like 12-15 hours a day because I was on a holiday. I was in Visakhapatnam, but I didn't have anything to do at home, so I've just been like sleeping, and it's going to have such adverse effects because I also need to get a haircut. Look how homeless I look. Yeah, that's a different problem.
As the data they hold, storage hosting solutions for data lakes
Maybe we'll
come in
finish
different
this
forms,
chapter and
each offering
close it.
unique benefits to different requirements. Let's explore the different hosting solutions available. Traditional on-premises storage solutions involve physical infrastructure located within a company's data center. On-premises offers full control over storage environment, which is relevant for industries with high security and compliance requirements. The strengths of this approach are enhanced security and control over hardware, potentially better performance for localized data processing. In terms of use cases, this is most often seen in highly regulated industries like finance and healthcare, where data sovereignty and security are the #1 priority. Cloud storage provides scalable and flexible data storage options hosted on external platforms, provided by vendors such as Amazon Web Services, Microsoft Azure, or Google Cloud Platform. The strengths of this approach are scalability, cost-effectiveness, and accessibility from anywhere. Cloud storage also offers various services that can be integrated, such as AI and analytics tools. Additionally, it transitions costs from CapEx to OpEx, making expenses more predictable and manageable. In terms of use cases, cloud storage is used in startups and enterprises needing scalable and flexible solutions without the overhead of maintaining physical infrastructure. Hybrid solutions combine on-premises and cloud storage to leverage the benefits of both environments. This approach allows you to keep sensitive data on-premises while using the cloud for less sensitive data. The strengths that this approach offers are flexibility, scalability, and the ability to keep critical data in-house while still benefiting from cloud technologies. In terms of use cases, hybrid storage is great for companies transitioning to the cloud, those with dynamic storage needs, or requiring a balance between compliance, security, and scalability. Multi-cloud strategies avoid dependence on a single provider and optimize storage based on different geographical and computational needs. This is achieved by using storage resources across multiple cloud platforms. The strengths of a multi-cloud storage solutions are risk mitigation, avoiding vendor lock-in, optimizing costs, and improving performance by locating data closer to users. This solution is great for large enterprises looking to enhance business continuity, optimize costs, and serve to global audiences. As you can see, the choice of where to store data in your data lake depends on several factors, including data types, volume, regulatory requirements, and specific business needs. The good news is that there are solutions for every need. When it comes to storage, so far, we have talked about how to store data in a data. There are solutions for every need. When it comes to storage solutions for data lake, Amazon S3, Google Cloud Storage, and Azure Blob Storage lead the market for cloud-based options. For on-premises setups, Hadoop HDFS is a popular choice. Let's explore these technologies in detail. Let's start with the most popular solution for data lakes, Amazon S3. S3 is a scalable object storage service that offers industry-leading durability, availability, and scalability. It is designed to store and retrieve any amount of data from anywhere on the web. S3 provides comprehensive security and compliance capabilities that meet even the most strict regulatory requirements. It supports data lifecycle. S3 provides comprehensive security and compliance capabilities that meet even the most strict regulatory requirements. It supports data lifecycle management and automated archiving features, making it highly cost-effective for long-term data storage. It is ideal for companies of all sizes that require high availability and robust data protection. It is commonly used for web hosting, data archives, disaster recovery, and, of course, for the storage layers of data lakes. Google Cloud Storage is known for its high performance and reliability. It integrates with other Google Cloud services, offering easy access to data analytics and machine learning tools. It offers a straightforward pricing model, and its network infrastructure ensures excellent data transfer speeds. Google Storage is quite versatile, supporting both SQL and NoSQL databases for diverse application needs. It is suitable for companies looking to run advanced data analytics and machine learning directly on the stored data. It is also great for storing and distributing large media files due to its high speed and low latency network. Azure Blob Storage is Microsoft's object storage solution for the cloud, due to its high speed and low latency network. Azure Blob Storage is Microsoft's object storage solution for the cloud. Blob Storage is optimized for storing massive amounts of unstructured data, such as text or binary data. Azure Blob Storage offers multiple data redundancy options and an excellent security model that includes managed identity and access management solutions. It is also integrated with the Azure Active Directory and Microsoft extensive analytics and AI tools. It is ideal for enterprises embedded in the Microsoft ecosystem and is particularly beneficial for storing huge volumes of unstructured data, backup and restore services, and serving images or documents directly to a browser. Hadoop HDFS is an open-source, distributed file system that is designed to run on commodity hardware. It is a component of the Apache Hadoop ecosystem and is tailored for handling large-scale data processing. HDFS excels in its fault tolerance and scalability. It is designed to store very large files and distribute them across multiple machines, ensuring high availability. It also integrates with other Hadoop ecosystem tools, such as MapReduce and Hive, making it a versatile solution for big data analytics. It is ideal for organizations dealing with massive data sets that need to be processed in parallel across many servers. Yes, you guessed it. Choosing the right storage solution for your data lake depends on your specific requirements and the provider your company is already using for other applications. The good thing is that there are robust solutions for every need. So once you decide on your storage strategy, the next important thing to think about when designing a data lake is the folder structure. Folder hierarchies help you organize data in a structured way, making it easier to navigate, manage, and retrieve. A well-thought structure is so important in environments like data lakes, where data diversity and volume can quickly lead to chaos. Let's take a closer look at some of the benefits of applying folder hierarchies in your data lake. Efficient folder structures reduce the time and computational resources needed to locate and access data. A good structure also simplifies the application of management policies, such as data retention, archival, and lifecycle management. It also enables the enforcement of security policies at the folder level, incredibly important for compliance and data protection. Creating an effective folder hierarchy in your data lake involves understanding the nature of the data, the needs of the users, and the operational dynamics of your company. Let's discuss some guidelines and considerations. The foundation of a good folder hierarchy is logical grouping, which categorizes data in a way that aligns with how users interact with it. You can use the following criteria for grouping. Organize data based on where it originates, such as from internal applications, social media feeds, or IoT devices. You may also group data according to business functions it supports, such as sales, HR, or operations. It's also important to think about separating data based on confidentiality and access requirements to streamline security management. Another powerful concept to consider when designing your data lake is the medallion architecture. This approach organizes data into different layers, typically bronze, silver, and gold. The bronze layer is where raw data is ingested from various sources. It's stored in its original format and is often used for historical records. The silver layer contains clean and enriched data. Transformations are applied here to make the data more usable for analysis. And the gold layer is the final, highly curated data layer. It is optimized for business intelligence and analytics, often containing aggregated and business-specific data. This is the structure we will use for our Capstone project. Another aspect you should take into account is to design hierarchies that are flexible enough to accommodate future changes in data volume, new data types, and evolving business needs. Create a modular structure where new categories can be added as new data types and sources come into the data lake without disrupting existing structures. Also, balance the depth and breadth of the folder structure to avoid overly deep navigation paths, which can complicate data consumption and management. Consistency in naming conventions and structure layouts ensures that the data is stored in a predictable manner, reducing errors and potentially improving automation. These are some of the strategies you can apply. Establish and enforce standard naming conventions that include clear, descriptive names for folders and subfolders, and integrate metadata tagging practices within the folder hierarchy to help with data discovery and governance. Let's see how some subfolder strategies may look in practice. For data related to specific projects or marketing campaigns, structure folders according to project names or campaign identifiers. For data that is time-based, such as logs or transaction data, organizing folders by year, quarter, month, or day can significantly. For data that is time-based, such as logs or transaction data, organizing folders by year, quarter, month, or day can significantly speed up queries that are time-specific. We will expand on this particular strategy once we discuss data partitioning in an upcoming video. There you have it. Designing a good folder hierarchy that works for your use case can have an impact on several important aspects of a data lake, particularly on accessibility and management. In data lakes, file formats determine how data is stored, accessed, and analyzed. The choice of file format can affect everything from cost to query performance. Let me share with you some of the most common used file formats in data lakes and why choosing the right one matters. CSV is one of the simplest and most widely used file formats. I'm sure you have used it in one way or another. It is text-based, easy to understand, and supported by almost all data processing applications. However, because CSV files lack any type of data compression or schema enforcement, they are not optimized for large datasets or complex queries. JSON files are highly flexible and support a hierarchical, semi-structured data format, which is ideal for data in varying schemas. JSON is extensively used in web applications and for exchanging data between servers and web clients. While JSON is easy to read and flexible, it can be less efficient for storage and querying large datasets. Apache Parquet is a columnar storage file format optimized for use within data lakes. It offers excellent compression and encoding schemes, which reduce storage overhead and improve query performance by allowing efficient reads for specific columns. Parquet is particularly well suited for complex nested data structures and is widely used in big data processing frameworks like Apache Hadoop, Spark, and Presto. We will use this format with a twist in our capstone project. ORC is another columnar storage format that provides a highly efficient way to store and process data. Like Parquet, ORC supports advanced compression and encoding, which makes it ideal for high-speed queries. ORC files are designed to work well in environments that require heavy read and write operations, making them popular in systems that perform frequent data updates. Apache Avro is designed for data serialization, providing compact, fast binary data format. It also supports schema evolution, where schemas are stored within the data, allowing serialized data to be easily integrated with applications. Avro is a good choice for data pipelines that require robust, complex data structures and fast data ingestion. Choosing the right file format in a data lake is so important. That's why there are so many sophisticated ones. As we saw, each file format offers different advantages and can be the best choice depending on your specific. Requirements. CSV and JSON are excellent for simplicity and flexibility. On the other hand, Parquet, ORC, and Avro provide better performance and efficiency for large-scale data operations. While this may be optimal for storage, remember that you can add almost any file type to a data lake, and that's the beauty of it.
We can try doing that. I don't think I have this. Being shared. I'm trying to run this code. Okay, 434 MB. We'll continue the codes.
With the volume of data stored in data lakes, we certainly need to think about data compression. Data compression is a technique used to maximize storage efficiency, reduce cost, and speed up data processing. By compressing data, you can store more information in less space and enhance the speed of the data transfer across networks. Let me explain how data compression works in data lakes. Data compression reduces the size of data files without losing the original data integrity. It can be performed using two main methods. Lossless compression compresses data in such a way that it can be perfectly reconstructed from the compressed data. It is used in data lakes where accuracy and data integrity are important, such as in financial records or historical data. Lossy compression reduces file by permanently eliminating redundant information, which is ideal for some media files like images and videos, where a slight loss of quality is acceptable in exchange for significant reductions in file size. You may be wondering, what are the benefits of data compression aside from occupying less storage space? There are three main advantages to think about. Compressing data means fewer storage resources are used, which can lead to significant cost savings, especially in cloud data lakes. Compression can also improve performance by reducing the amount of data that needs to be read from disk during queries, which is particularly beneficial for read-intensive applications. Compressed data also requires less bandwidth to transfer, speeding up data ingestion and replication processes across distributed systems. Now let's talk about specific compression formats. I'm pretty sure you have heard about some of these. Zip is widely used for lossless data compression. It is ideal for text and numerical data, which are common in corporate environments. Snappy and LZO are fast compression and decompression algorithms, making them suitable for real-time data processing in data lakes. And finally, gzip provides a good balance between compression ratio and speed, commonly used with text data in log files and other types of large datasets. When implementing data compression in a data lake, it is very important to choose the right format based on your data type and processing needs. For instance, columnar formats like Parquet or ORC compress data by default and are optimized for analytical querying, making them excellent choices for data lakes used for business intelligence and analytics. Of course, there are also some considerations to think about regarding compression. Sometimes less is more. First, understand the trade-offs. Higher compression ratios can sometimes lead to longer decompression times, which might affect performance during data retrieval. Next, align compression with usage. Compress data in a way that aligns with how it will be accessed and used. Frequently accessed data may benefit from lighter, faster compression to speed up read times. Lastly, monitor and adjust. Regularly review your compression strategies to ensure they continue to meet your storage and performance needs as your data lake evolves. Data compression is a powerful tool for managing the scale and complexity of a data lake. By understanding and implementing the appropriate compression techniques, you can optimize storage, improve performance, and reduce operational costs. Data partitioning is one of the most important aspects of data organization in a lake. Partitioning is the process of breaking down data sets into more manageable parts. The partitioning can be based on different attributes. By scanning only relevant partitions, query performance can be significantly enhanced. Efficiently organizing data by partitioning can ultimately lead to reduced storage and computational costs. These are the different types of partitioning that can be applied in data lakes. The first one is horizontal partitioning or data sharding. It involves dividing a dataset into rows or records. This type of partitioning is beneficial when data can be easily segmented by a specific attribute, such as a geographical location or department. Next is vertical partitioning, which involves splitting data into columns. This is useful when queries access only a subset of data fields frequently. And functional partitioning is where data is partitioned according to its function or usage within the business process, such as operational data versus historical data. Now, let's look at some partitioning strategies that are frequently applied. Partitioning by date is one of the things that can be applied in data. Data partitioning is one of the most important aspects of data organization in a lake. Partitioning is the process of breaking down data sets into more manageable parts. The partitioning can be based on different attributes. By scanning only relevant partitions, query performance can be significantly enhanced. Efficiently organizing data by partitioning can ultimately lead to reduced storage and computational costs. These are the different types of partitioning that can be applied in data lakes. Based on different attributes. By scanning only relevant partitions, query performance can be significantly enhanced. Efficiently organizing data by partitioning can ultimately lead to reduced storage and computational costs. These are the different types of partitioning that can be applied in data lakes. The first one is horizontal partitioning or data sharding. It involves dividing a dataset into rows or records. This type of partitioning is beneficial when data can be easily segmented by a specific attribute, such as a geographical location or department. Next is vertical partitioning, which involves splitting data into columns. This is useful when queries access only a subset of data fields frequently. And functional partitioning is where data is partitioned according to its function or usage within the business process, such as operational data versus historical data. Now, let's look at some partitioning according to its function or usage within the business process, such as operational data versus historical data. Now, let's look at some partitioning strategies that are frequently applied. Partitioning by date is one of the most common strategies, and is especially useful for time series data. Data is divided into partitions based on time intervals, which can be daily, weekly, monthly, or yearly. This strategy facilitates efficient access to time-bound data. An example is log data, which could be partitioned by date to allow analysts to query data efficiently based on specific dates. Another strategy you can apply is partitioning by business logic. This strategy can be useful for multi-tenant systems where data is segmented by customer or business unit. This type of partitioning enhances data security and access control by isolating data relevant to a specific business unit or customer group. For example, a multinational corporation may partition sales data by country or region, and this can improve access speed and relevancy for regional analysts. Now let's discuss some best practices when it comes to implementing data partitioning. First, make sure that the rules for partitioning are clearly defined and aligned with the data access patterns and business requirements. Next, you can regularly monitor the performance of partition data and adjust the strategy as needed to accommodate changing data volumes and query patterns. Also, be mindful of data skew, where some partitions may end up significantly larger than others and could potentially degrade performance. In the context of a data lake, especially one using file systems like HDFS or cloud storage, like Amazon S3 or Azure Blob Storage, partitions are often represented as folders in the underlying file system. Each partition may correspond to a specific folder containing files relevant to that partition. Now let's take a look at how this is implemented when using some of the most common technologies. Apache Hadoop HDFS supports partitioning at the directory level, where data files can be organized into folders that represent different partitions. This means it allows for manual partitioning by creating directory structures that reflect partitioning logic, such as by date or region. Hive is a data warehousing tool built on top of Apache Hadoop, providing a SQL-like interface for querying data stored in HDFS. Hive supports automatic partitioning by allowing you to specify partition keys when creating tables. Data inserted into this table is automatically stored in partition folders based on the partition keys. S3 supports partitioning through the use of prefixes and directory structures within buckets. Folders are typically named after partition keys and their values. For example, if data is partitioned by date, you may see a folder structure like the one in the image. With this method, data belonging to the same partition in this case all data from the 25th of December 2021, is stored in the same folder. Tools like AWS Glue can be used to manage metadata and optimize how data is queried from S3. Spark is a unified analytics engine designed for large-scale data processing. Spark supports dynamic partitioning during data processing, which can be configured through its data frame and dataset APIs. During data transformations and actions, Spark automatically partitions the data, which can then be written into S3 in a structured format. Here's a basic example of how to implement partitioning in S3 with Spark. First, we load the data into a data frame. Then we can perform some transformations, and then write it into S3 with partition by year and month. Good partitioning is key to making storage and retrieval in data lakes work better. By carefully selecting a partitioning strategy, you can keep your data lake efficient, cost-effective, and in tune with your use case needs.
This is a fun chapter. I have some doubts. What does this mean? Okay. After spending so much time studying and summarizing, if I don't get all 13 of them right, it'll be a shame. But it'll be a shame, but also it's been a tricky chapter, is what I feel. Transaction data from second quarter of a year. JSON. Let's go. Let's go. This is what Fivetran does, so I'm excited. I'm not excited because I feel like I would know everything in this chapter, but we'll do it anyway. But I think I'll pick this up tomorrow. There was something else that I wanted to, I wanted to understand what is like commodity hardware. Okay. There was something else that I wanted to like check. I don't want to redo my questions. There was something that I wanted to do. I want to understand difference in Parquet and ORC. Oh, Gemini is better. This is dumb because it didn't even add JSON. Let's see what Gemini does. I'm just curious. Gemini generates better images is what I feel. I can generate this. just because it will be fun. What is that? Whimsical. Okay. I think that whole activity was a waste of time. I think we're good. Okay, there was actually one other thing that I wanted to do. So I have a mentoring session next week, and I wanted to make a. So there was an activity where I wanted to. So there's like various strengths and weaknesses. You have a PM, and I wanted to list down my own strengths and weaknesses so that my mentor can start working with me on improving my weaknesses, and then maybe yeah, maybe we can also work into turning these strengths into superpowers. There's actually a video by Shreyas Joshi that I want to see, and then do this activity. Twenty-year experience is wild.
The core difference between a good team and a great team is the judgment of the leader of that team. That's
What do I think this is an average area? And this is good. This is what I wanted to. I have two average areas. I need to make them into decent areas, and the weakness. So everything needs to go to a leveled up. Weakness should be a decent one. Averages should be. Weakness should be an average thing. Weaknesses should be an average thing. Average thing should be decent. I don't think I have to touch. Strengths I have to make into superpowers. Okay, this is good. Okay, what else do we do? Okay, I was actually reading a book. It's called Tipping Point. Let me actually quickly grab it. So this is the book. I've been reading it. I feel like it's a decent book. I wouldn't call it a great book because not that fun, but decently fun. So maybe I'll continue reading this. It's already 11 o'clock. So I think good stream. Good to be back. What did we do? We did. Actually, let me quickly fill up my stream agenda because if I don't do it, I'll forget it. And I also didn't put this stream on YouTube, which is sad, but stream agenda because I did this course. Oh, where is that course? Oh, I did chapter 1 and chapter 2. Again. And I also did this. Completely authenticate. Oh, this is what I don't think it's a lot, but it's a start. We will soon do better, but I think that is it for this stream. Let's go. Let's lock in.